So meaning that you can actually move an object, can move to the left, can move to the x, to the y, to the z, to the y. So you can actually move in all these three directions. And then this object itself can also rotate in all three directions along the three principal axes. So you have 6 degrees of freedom. And the question here is, when we talk about the joint, so what happened here is we actually mentioned that we are going to have 1 degree of freedom joint. And then we argue that no matter what type of mechanism you have, you can actually reduce them to a sequence of 1 degree joint. So for this object, if I restrict to 1 single degree of freedom, so meaning that if I only can turn in this direction, so I can only do a row. So meaning that I can no longer move x and y, cannot move x and y as well as z. So meaning that the 3 degree of freedom for the translation is lost. You can only rotate. You can only do a row. You can only do a row. You can't do a pitch, and you cannot rotate along the y and z. So what happened here is you again lost 2 degrees of freedom. So you only left with 1 degree of freedom. So the 5 lost degrees of freedom are the 5 constraints. So you have your 6 degrees of freedom minus 5 constraints, so you left with 1 degree of freedom. So this is why we have here, 1 degree of freedom joint, you have your 5 constraints. So what happened here is you have n moving lane, so you have your 6n parameter, 6 degrees of freedom, and 1 degree of freedom joint, so you have 5n constraint. So the degree of freedom of the system, you can actually simply calculate by 6n minus 5n, which is actually equal to n. So this n is essentially the number of joints of your manipulator. So if you count the number of joints of your manipulator, you very likely you will actually be able to find the degree of freedom of the manipulator. So in this case, we have an n effector over here at one end, and on the other end, we actually fix. So meaning that this link is fixed. It doesn't move anywhere. So what happened here is, if this link is not fixed, if the base is not fixed, so meaning that the base can actually do 6 degrees of freedom, so you will have n plus 6. But in this case, but for our purpose, we don't really consider that. But what happens is, if you have a humanoid robot, so the base can be moved around, and then you're likely to have the 6 degrees of freedom. It will become a lot more complex. So we have mentioned this. So the degree of freedom is something that you need to be clear of. And then the other thing that you need to be clear of is the right-hand coordinate systems. The right-hand coordinate systems, meaning that if I have if I have this x, this is y, I'll be able to find the z positions. So you use your right hand, you'll be able to tell the directions. So when you actually fix a coordinate system on a frame, on a link, you specify your x and y, and then the z you'll be able to tell your z. So a lot of time you can actually you have to use your right hand. So this is called a right hand coordinate system. So if you move from the x, to the y, the term will actually give you the x from x to y. The term will actually give you the z direction. Okay. And then one more thing before we move on to chapter 1 on the kinematic is, I would like to do a quick review on the trigonometry identity. So I believe all of you have last week you have actually looked through the linear algebra. And then you'll see that the linear algebra is actually a very important component of this course. So for today's course, you probably will need to know a bit of trigonometry. So these are the typical rotation matrix. So this rotation matrix actually assumes a right-hand coordinate systems. So Rs theta, meaning that you rotate at the angle of theta with respect to the x-axis. So this is your cosine theta, minus sine theta, cosine theta over here. So this is your x rotation matrix This is your Y rotation matrix. This is your Z rotation matrix. And then these are some identity you should know. Like for example, sine theta is equal to cosine theta minus 90 degrees. If you have browsed through the lecture notes, you will see that instead of writing cosine theta or sine theta, we actually have x theta. So the x, if you happen to see s theta, so it meaning that this is sine theta. So because there are so many of them, sine theta, cosine theta, and so on, so it's easier to actually simply just write it as s theta. It makes it a lot more simple as well. Okay, then you have all this sine, you have this cosine theta 1 plus theta 2. So cosine theta 1 plus theta 2, we write as C12. So if you happen to come across C12, it actually means that this is cosine theta 1 plus theta 2. So you may actually come across S123. So it means sine bracket theta 1 plus theta 2 plus theta 3. So you have a set of other identity where you have your cosine square theta. This is cosine square theta plus sine square theta equal to 1. Okay? So this is a trigonometry. And then take a quick look after the lesson. Now we move on to the chapter 1. So we move on to chapter 1. We are going to deal with the kinematics. So these are the topics that we are going to go through. So we're going to talk about position, orientation, and continuous transformation, the homogeneous transformations, other orientation representations, and then we have the kinematic modeling of the manipulator arm, which is a DH notation, forward kinematics, inverse kinematics. For today's lecture, I hope to complete 1, 2, and 3. But if I'm going too fast, please let me know. Okay? So the first thing is the position, and the first section is on position and orientations. So for example, you have a manipulator over here, there's a cup. And then the manipulator need to know, is asking where is the cup, so that the manipulator can actually go on and pick it up. So in order to do that, you can attach an eye, you can attach a camera, on the manipulator. So this is called eye in hand. So you have your camera, and your camera will be able to see the cup. And then you can also have something called eye to hand. So what happened to eye to hand is the camera is actually at an external position. So it's actually not attached to the manipulator arm. So eye in hand and eye to hand both have its advantage and disadvantage. But the problem here is, you see something, it doesn't mean that the robot will know where is it. You need to tell the robot where is the cup. So you have to describe where the position. You have to describe the position and orientation. So this is the topic for the first half of today's class. So to describe the position and orientation, we are talking about description. So position and orientation is within the space. So this is also known as the spatial description. The word spatial over here simply means that it's space. So you have your description. So you have to describe where is the object, the attribute of the object, so that the manipulator can deal with it. You also need a transformations. You need a transformation because even if you're going to put your camera on the robotic hand, on the robotic manipulator, they are separate entity. So you need, and then on the image is on the camera itself, you capture an image. The image has its own coordinate system. So you need to have a set of transformation so that all of them are within the same coordinate systems. So you need to go through a process called transformations. So a definition of transformation is a process by which one expression or function is converted to another with similar value. So the spatial description, we need to specify the spatial attributes. And then for our Turing, we are actually using something called a Cartesian coordinate frame. So Cartesian coordinate frame, the right hand, you see the right hand coordinate system that we see just now. That's an example of a Cartesian coordinate frame. So all the Cartesian coordinate frame in this course will probably be using a right hand coordinate systems. So when you actually move on, to do robotic vision, you may actually find that the image itself may not be actually be defined, will have its own, may have a coordinate system that's actually deviate away from the right-hand coordinate system. But the one will not be, but we will not be covering that. It's not within the scope of this module. So when we actually talk about the spatial description, we want to know the position as well as the orientation of a rigid body. So I mentioned that the cup is a rigid body. There's a difference between a rigid body and a soft body or flexible body, meaning that a rigid body is rigid. So it does not deform. We talked about that last week. So you have to tell the location of a rigid body. You have to specify its position. So meaning that it's X, Y, Z. And then you also need to know the orientation of the rigid body. So if we have a specific point, so this particular point over here, we refer to this coordinate frame. If you look at this coordinate frame from X to Y, the Z is actually pointing upward. This is an example of a right-hand coordinate systems. So you have a reference frame. So a reference frame is your global frame, is what all the things that's actually going to be based on. So you have a point. So this position vector will have to be written with respect to this coordinate frame. Sorry. So to represent the point, you have P, you have A, P. So the A over here implies that this P is actually with respect to this coordinate frame. And then we represent the coordinate frame with a bracket A in this manner. So the point P will actually be represented by 3 parameters. So you have your Px, Py, and Pz. So this is belong to a set of real number with a dimension of 3. So as for the attribute of a body, it also have to refer to some reference frame. So this is a rigid body. So you have the rigid body have to make reference to a frame. So same thing, we have the frame A over here, and then we attach a frame on the body. So in this case, we attach a frame B on the body to actually represent the orientation of this body. So by attaching this coordinate frame B to the body, we actually give a description of this coordinate frame relative to the reference coordinate frame. So the way we write it is we will be writing it as A, B, R. So it's actually representing a rotational matrix specifying the relationship between the frame A and frame B. So you have your AXB, AYB, AZB are essentially, these are all unique vectors. So ABR is equal to a set of 3 column vector. So you have your AXB, AYB, AZB belong to a set of real number 3 by 3. So 3 by 3, so meaning that there's actually altogether 9 elements over here. So we have, so this is a bow X. So bow X, bow small x, we actually use it to represent a vector. So a lot of time, so actually if you look at this position vector itself, so a lot of time we actually use a column vector to represent a point. And then if we have this, we have this A, B, R, AX, B, AY, B, AZ, B belong to a set of 3 by 3. To quantify this as a representative metric, the AXB, AYB, and AZB have to be an orthogonal unit vector. So when you have an orthogonal unit vector, what happens here is you have an orthonormal matrix. So the orthonormal matrix meaning that the determinant of this orthonormal matrix the determinant of this orthomatrix ABR will actually be equal to 1. And this one is going to be the positive 1. And you have to be following the right-hand coordinate frame. So when I write AXB over here, it actually means that the XB is expressed in frame A. So always remember the upper subscript will actually be used to represent the reference frame. So, and then bear in mind that the multiplication of the rotation matrix generally will not be commutative. So not commutative meaning that if I multiply R1 by R2, it's not the same as multiply R2 by R1. So the order of multiplications is important. So if we continue, ABR, which is comprised of AXB, AYB, and AZB, if we actually expand it out itself, you can actually see that the AXB is essentially equal to, the XB is essentially equal to XB dot AXA, XB dot AY, YA, XB dot ZA. And then the AYB will be YB dot YA, XA, YB dot YA, YB dot ZA. Similarly, you have this AZB equal to this dot product. So if you look at last week's review on linear algebra node, you will know that the A dot B, A and B are vector, will actually be equal to magnitude of A multiplied by magnitude of B cosine theta. So what happened here is these three vectors, the XA, YA, the XB, YB, and YZ are essentially a unique vector. So when they are unique vector, meaning that the magnitude is actually equal to 1, so your XB dot XA will actually give you the cosine theta. So meaning that all the components are essentially the directional cosine. When you assign the frame, it can be arbitrary, but it should be the same throughout. So on the other hand, you can actually observe that the rows of the matrix are the unique vector of A expressed in B. So essentially, this is a transpose object A expressed in B. So with that, you can have the ABR is actually equal to BXA transpose. So the T over there indicates that this is a transpose. So your ABR is BXA transpose, BYA transpose, BZA transpose. So this is a column representation. And then if you actually express it in the form of row, so you will have BXA, BYA, BZA transpose. So if you look at this BXA, BYA, BZA transpose, you are essentially having a rotation matrix BAR. So meaning that you have a rotational matrix of A expressed in terms of B. And then follow with a transpose. So your ABR is equal to BAR transpose. So if we follow the convention nicely, this is what we get. Okay? So if we have the description of frame A relative to frame B, so description of frame A relative to frame B, so always remember that the B over here, the upper one, is a reference frame. So BAR will be equal to ABR transpose. So what this suggests is your ABR invert will actually be equal to ABR transpose. So how do we prove that? Simple. We know that if I multiply a matrix which is invert, I will actually get the identity matrix. So this is the identity matrix. So if I have your ABR transpose multiplied by ABR and multiply them together, I will actually end up with an identity matrix. So this identity matrix is I3. The 3 over here just simply implies that it's a 3 by 3 column. It's a 3 by 3 matrix. So the inverse of a matrix with orthonormal column is equal to its transpose. Okay? So what happened here is we actually see that this is unique. So this ways of representing the orientation is unique. Of course, you can attach a frame here or here or at the corner and so on, but eventually you will have unique representations. So this is unique, and then you only have 3 independent parameters. So the orientation is the 3 angle. And then the matrix itself will have 9 elements. So you have RR11, R12, R13 to R33. Okay? So the rotation is actually within the 3, it's only with respect to the 3 angle. So you do some elementary thing. So you look at the rotation about AXO by angle theta. So this is a right-hand coordinate frame. I have a matrix. So this rotation matrix A1, we refer to A0. So this is we refer to A0. The rotation matrix will actually be given. If I'm to rotate along the x-axis, so along this x-axis, this is my rotation matrix. So you have your 1, 0, 0, 0 sine theta, 0 cosine theta, minus sine theta, sine theta, cosine theta. So your Z A1. So you actually, so we assume that the 2 axes, the 2 coordinate system, the ZA1, the A1 and A0, they initially coincide. So meaning that they initially coincide, and then after that, this is the initial condition that we actually first assume. So the A1 and A0, they are initially coincide. So they are initially coincide, and then so to rotate along the x-axis by angle of theta, you have this rotation matrix. And then to rotate an angle theta, same thing, we assume the A1 to coincide with the A0, and then we are going to rotate about the YA0 by angle theta. You will actually have you arrive at this rotation matrix. This is also written as RY theta. And similarly, you have one for the z-axis. So A0, A1. So you rotate about the z-axis. So this is the z-axis. You rotate an angle of theta. So this is the angle of theta. So RZ theta. So you have cosine theta, minus sine theta 0, sine theta, cosine theta 0, 0, 0, 1. Okay, so these are fundamental. And then so once we have attached a frame to the object, and then we have the frame is a description of both position and orientation of an entity or rigid body. How do we actually represent the frame location and orientations? So we actually need to use a set of 4 vectors. So the 4 vectors will give the position, so which is typically the origin, as well as the orientation information of the frame relative to the reference frame. So meaning that if I have a B over here, we refer to A. So this is the box. So imagine this is the box that we have just now. So you have this. That actually you have one more vector, the APB origin, that actually relate them. So the APB origin is a vector indicating the translation of this origin A to B, and then followed by rotations. So the frame B, so this frame B is relative to frame A, and it will be described by this transformation. So you have your ABR. So this is the rotation metric that we go through just now. And then we have this APB origin, which is a translation vector. So the rotation metric comprises of 3 vectors, and then you have this translation vector, that's another one single vector. So altogether you have 4 vectors. Okay? So now we move on to coordinate transformations. So there are various ways of looking at interpreting a coordinate transformations. So the first way we look at is we consider it as a mapping. So when we consider it as a mapping, we are changing the description from a frame to frame. So from a frame to frame. So for example, if we are going to express the position vector of a point in space in terms of the various reference coordinate system. So if I have a point P with reference to this coordinate frame, so I'm given PB. So a BP, the BP over here meaning that this point, the coordinate is given with respect to this coordinate frame. So I want to determine the same point B with reference to coordinate A. So this is P, this is AP. So with that, you have your, so in this case, it involves a translate frame. So if both of the frames have the same orientation, so essentially there's no rotation metric. The rotation metric is actually your identity metric. So what happened here is your AP is equal to your BP plus AP B origin. So which is the translation of your origin. So your AP is equal to BP plus the translation of the origin. The translation of the origin. AP B origin. So this is applicable when the orientation of both frame A and B are the same. So what happens is we have a rotated frame. So a rotated frame meaning that both the A frame and B frame are initially coincident. So meaning that they are initially aligned. The axes are initially aligned. We have a point P. So this point P, and then B is rotate along X. Around X. So you have this. So they are no longer aligned. So the two axes are no longer aligned, and then you are given a P with respect to coordinate B frame. So you have the coordinate of B, P in B, so your BP. So you want to determine your P in A. So this same point in the A coordinate systems. So in this case, you just need a rotation. You just need the rotation matrix. Just need a multiplication of the rotation matrix. So when you actually look at the multiplication of the rotation matrix, you can actually visualize that the B and B will cancel off, so you end up with PA, AP. So the upper subscript and the lower subscript of the parameter on the right get cancelled off, then you will actually end up with AP. So this is one way of verifying that you actually have the right transformation. So this is coordinate of P in A. So what happens if the two origins are not the same? So you will actually have to deal with the translation. So you look at an example. So this is a simple example. So if I have figure 1-1, so a frame B, so this is a frame B, which is rotate relative to frame A about Z by 30 degrees. So if you look at this figure itself, where is Z? Remember, this is right-hand coordinate frame. So you move from X to Y. If you move from X to Y, so your Z will actually point out of the paper. Okay? So you have that. So you are going to rotate B. You're going to rotate. You point out the paper. There's a point P, whose position vector is expressed in B. So you have BP equal to 0, 2, 0. So this particular point B is 0, 2, 0. So 0, 2, 0. This is the x-axis. So this is at the origin of the z-axis. So you have your z-axis actually equal to 0. Your x-axis is equal to 0, and then you assume that this is actually 2 units along the y-axis. So this is on your y frame, on your B frame. So you want to determine what is the position vector of the point P expressed in A. So this point P, now with respect to this frame A, XA, YA. and ZA, which is actually pointing out the paper. So same thing. You know that this is a rotation about the z-axis. So you have your ABR, which is actually equal to the rotation matrix about the z-axis. So you have your cosine theta minus sine theta and so on the upper corner, and then this is the rotation matrix. So this rotation matrix along the theta, and then the theta is 30 degrees, so you actually end up with 0.866 minus 0.5, 0.5, 0.866. So you have given the point, the BP, so it's 0, 2, 0 transpose. So we mentioned earlier that we typically express a point vector, a position vector as a column vector. So this is why over here you see a BP equal to 0, 2, 0 transpose. So while this is a convention that's actually typically used, there may be cases where a point is actually indicated as a row vector. So make sure you study the context. You read according to the context. Okay? So once you have that, you have your AAP equal to ABR multiplied by BP. So B and B cancel off, you have your AP. So you do the multiplications, you will have minus 1, 1.7320. So meaning that this point, P, is at minus 1, x-axis away, and 1.732 along the YA, and then of course it still remain on the z-axis plane, on the xy plane. The z is actually equal to 0. So I think these are simple stuff. We can move a bit faster. So what happened here is we have your ABR is essentially acting a mapping, which is to describe P relative to frame B given BP. So the original vector P does not change. So bear in mind that the point doesn't change. We simply compute the new description of a vector relative to a new frame. So the P is not moving at all. What about a general frame? So a general frame meaning that the B will actually have an orientation as well as a translation, just like the first example that we actually use. So in this case, I'm given BP. So this P, BP. So this P is actually the coordinates we refer to this coordinate frame B. So I'm given BP. So I want to find AP. I want to find this point with respect to this frame A. So same thing, we can visualize that we have an intermediate frame. So this intermediate frame is A prime. So this intermediate frame will actually involve. So you have this intermediate frame A prime. So the A prime we refer to frame A. The rotation metric will actually equal to I3. So meaning that there's no change in orientations. So you have this I3. Then, but the frame B we refer to with respect to frame A prime. It's actually involve a rotations, a change in orientations. So this is actually equal to ABR. So there's a translation across. So the same thing. The A prime P will actually be equal to A prime B R BP, and the AP will actually be equal to AP B origin plus A prime P. So you have these translations. So you have this translation of the origin, and then this is the rotation matrix due to this. So you sum them up, and then you put them all together, you actually end up with AP equal to AP B origin, which is a translation, and then followed by the rotation of the frame. So this is A prime B, A prime R B BP, and then we know that the A prime B R is actually equal to your AB R, so you can actually simply put AP B origin plus AB R BP. Okay? So this is the final answer. We have your AP equal to AP B origin plus AB R BP. So we call this the AP B origin, the translational transformation, and then the ABR, the rotational transformation. ABR, BP, that's rotational transformation. Follow? Okay? Yeah, I guess it, yeah. So what we've gone through is simpler, is simply some transformation. And then now the next thing we actually move on, the matrices that we actually deal with is 3 by 3 matrix. And then what we're going to do now is actually we're going to move on to homogeneous transformations. So the problem with this 3 by 3 matrix is that for this transformation itself, the AP is equal to AP B origin plus AB R BP is involved in additions. So it would be nice if we can actually accomplish everything via metric multiplications. So this can be done if we express everything in the form of a homogeneous transformation. So meaning that we want to convert this form to AP equal to ABT BP. So what is the advantage of having a homogeneous transformations? You allow the writing to be more simple, the analytical analysis of the transformation a lot easier. But when you actually implement it on your computer, you may not want to do that. So because especially if you know that there's actually a multiply by 0. So it's for theoretical analysis. It's more for theoretical analysis than actual implementation. So you have this. So the next topics will be on homogeneous transformations. So same thing. If you are given the P with respect to the B origin frame, you want to know the PA with respect which is the point P, the coordinate of point P with respect to the reference frame. So for homogeneous transformation, we are not going to steer too much onto the matrix itself. We'll simply just say that if I have a vector, a BP vector, a P which is actually expressed in terms of the B coordinate frame, it will be BPX, BPY, BPZ, and then we will have one vector called augmented vector. So in some cases, this is actually known as a skew parameter. It's the skew factor. But in our context, we always assume that this is an augmented vector which have a value of 1. So a homogeneous transformation matrix itself, the ABT will now become ABR, AP, B origin. So this is a vector. This is a vector. It's a column vector of 3 elements. And then the last row itself, you simply add one more row. So this row will be 0, 0, 0, 1. So this 0 over here refers to a row of 3 0. So this is your rotation matrix, the rotation matrix that I've gone through just now, a 3 by 3 matrix. So after you have multiplied ABT with BP, you will be able to get AP. So your AP will be APX, APY, APZ, and 1. So this is a scalar quantity, a number. So what happened here is with homogeneous transformation matrix, you now have a 4 by 4 matrix and a 4 by 1 column vector to represent a point. So if I have a frame B, which is rotate relative to A, so this is A, by 30 degrees and translate 10 units in XA, 10 units in XA, and then 5 units in YA. So it's supposed to find the same point P with respect to frame A. So with respect to this frame B, so you are given that the P with respect to frame B, which is this frame, is 370. So it's straightforward. You apply what you have. You apply the formula that we have earlier on, which is this, the equation that we have the expression that we have earlier on. So this is the rotation matrix. So this is rotate about the z-axis by 30 degrees. So this is a rotation matrix. This is the translation vector. So translation vector 10, 5, 0. x is equal to 10, y is equal to z, and y is equal to 5, and z is equal to 0. You do the multiplication, you will actually end up with this value. So meaning that your point A, the P with reference to A, will have a value of 9.998 in the x-axis. So this is the x-axis. So this particular point itself, if you project it down onto the x-axis, will have this point will have this value will be 9.098. And then if you project this to the y-axis, which is along here, will be 12.562. So there's no change in the z value. So the z is actually equal to 0. Okay? So if you have learned this before, please bear with me. Yeah. So there are different ways of interpreting it. So one way of interpreting it is to say that this transformation T, this transformation T actually represents a coordinate transformation in a compact form. So you have essentially you have a change in the coordinate. And then the other interpolation is that the T actually represents a position and orientation of the coordinate frame B relative to A. So you can actually say that this is, I have one object here, and then move to here and then change. So this is a coordinate transformation. And then on the other hand, you can actually say that I have these two objects, and then these two objects, this T is actually representing the position and orientation of this frame with respect to the reference frame. The reference frame does not have to be the world coordinate frame. So you have a world of multiple objects. So it can be, so the reference can actually be between two objects. Okay, so the third one is that this T essentially represents a rotation and translation of the coordinate frame of A to B. So a rotation and then followed by a translation. Okay. So the rotation and translation actually imply that the A frame and B frame are initially aligned. You may come across a term called free vector. So for a free vector, the fourth element will actually have a value of 0. So when we say that a vector is a free vector, it's not a point or a line. It's actually something that can move freely around the space, but you have a fixed magnitude and a fixed direction. So an example of a free vector would be force, velocity, and so on. So in this case, the vector, you will actually augment the vectors with 0 rather than 1. Okay? So you may actually come across, so not all the time you actually have a 1 over here. So with the homogeneous coordinate system, we come to the homogeneous transformations. So the purpose of homogeneous transformation is to support something called a consecutive transformation. So to study, so if we actually look at a manipulator, earlier on in the first class we said that a manipulator consists of link, and then the base frame is fixed, and then you have the joint, and then after that you come to the next link and so on. So if we want to study the kinematic of the manipulator, we will need to attach a frame to each of the link, not the joint. So you have to remember that you have to attach a frame to each of the link. And frame I will be considered to be attached to link I, where I is from 0 to n. So this is 0 frame, which is your base frame. And then in your context, the base frame is usually fixed. And then you have this frame n. So the frame n will be your n effector, will typically be your n effector. And then you have this, so this is your n effector. And then this is the point P that the n effector is going to grab onto. And then in between all these, you have the link. So this is one link, this is another link. So you have to attach a frame to all these links. So this is one frame. So you have frame 0 attached to the base, and then you have frame 1, frame 2, frame 3, and so on, and so on. So if you are given an augmented position vector of P expressed in frame M, and then you are given the I minus 1 IA. So I minus 1 IA, meaning that the frame, the frame A, the matrix A, with respect to frame I minus 1. So meaning that it's a transformation that matrix that's actually linking, for example, 1 to 0, 2 to 1, and so on. So you have this NP and I minus 1P. You want to find OP. So meaning that you want to find the point P. You want to find point P with respect to the base frame. Given the point P with respect to the frame N, the N effector frame, you want to find the P with respect to the base frame. And then you know the intermediate transformation frame, transformation that's actually between the link. So this is the intermediate transformation link. But now what happened here is instead of writing as T, we are writing as A. Okay? So with that, you can actually express them as OP is equal to 0, 1A, 1, 2A, multiply N minus 1A, NA, AMP. So you can actually visualize it as one thing that where you can actually cancel off the N with N, 1 and 1 and so on. So at the end, you will actually end up with OP. So this is your OP. So when you actually multiply this 0, 1 to N minus 1 NA, this is essentially, you essentially have a matrix ONA. So this is your matrix. This is known as your consecutive transformation because you basically have one transformation multiplied with the other one. And then finally you have this ONA to actually representing them. So this is the homogeneous transformation from frame M to frame 0. So frame M with respect to frame 0. So when we will come across the DH, we'll talk more about the DH transformation later on. So the DH transformations will essentially meaning that the A matrix is a homogeneous transform with respect to the local joint coordinate. T matrix is a product of A1 to ATAN. We'll talk more about this next week. So you have a consecutive transformation in this manner. The next thing here is if I'm given ABT, so meaning that the transformation on B with respect to A, so I want to find BAT. So if you look at ABT and BTA, so this BAT is essentially ABT inverse. So you want to find the inverse of a homogeneous transformation matrix. So by definition, an inverse ABT multiplied by ABT minus 1 will actually be equal to I. So this is the definition of your identity matrix. So you move on. You know that you have your AB, your ABT will actually be equal to AB error, AP, B origin, 0, 1. So it's 0, 0, 0, 1. And then you are unsure of this ABT inverse, so you put the X, Y, 0, and 1. So the Y is actually a column vector, and then X is a 3 by 3 matrix. And then they are supposed to be equal to, they should equal to identity matrix, a 4 by 4 identity matrix, meaning that you have 1, 0, 0, 0, 1, 0, 0, and so on. So you break this up itself. This is actually contribute your I 3 times 3. So this is identity matrix, 3 by 3 identity matrix. And this is your translation vector, your 0 vector, which is 0, 0, 0. So 0, 0, 0, 1 is always there. So from here itself, you know that the RA, the AB error multiplied by X is equal to I. So meaning that your X is equal to AB error inverse. And then the ABR inverse, we have verified earlier that the ABR inverse will actually be equal to ABR transpose. So ABR transpose meaning that you have your BAR. So your X over here is equal to your BAR. And then next you look at this. So you have your ABR multiplied by Y plus the BO origin multiplied by 1 will actually be equal to your zero column vector over here. So this is a 0 over here. So this is what you have. Then your Y will actually be equal to this bring over and divide by this. Your Y will actually be equal to minus ABR inverse APB origin. So again, this is equal to transpose. You have minus ABR transpose AP origin. This is just some manipulation. So with that, the inverse of a homogeneous transformation matrix T, BAT, will actually be equal to ABT inverse is equal to ABR transpose minus AB transpose R transpose APB origin. And then you have the lower vector comprised of a set of 0, 0, 0, 1. Any question? Okay, good. No question. Yeah. It's just a matter of complementarity. So this is a basic. So you'll keep referring to it. We'll look at an example before we take a break. Sorry. Yeah. Okay, figure 1.5. So this figure 1.5 shows a frame B, rotate relative to frame A, about Z. So we know that the Z is actually pointing out of the paper by 30 degrees, and translate 4 units in XA, and 3 units in YB. So you're supposed to find BAT. So you're supposed to find BAT. So you want to find the BAT, which is the inverse, but you know the ABT. So ABT will actually comprise of a rotation matrix, the ABR, and then followed by a translation matrix, just translation vector. So this is the matrix ABT. So the BAT will actually be equal to your ABT inverse. So ABT inverse, we know that this is equal to ABR transpose minus ABR transpose AB origin. So this is transpose. So you actually take this as a transpose. The transpose meaning that the 0.866, 0.50 over here will become 0.866, 0.50. And then minus 0.866 will be minus 0.5, 0.866, 001 will be 001. So you got your transpose quite easily. So with the transpose, you multiply with the position vector, and then with the minus signs over here, this is what you end up with. Okay? Okay, we take a break. Can we resume? We take a break. We'll resume the class at 7:10. Okay. Yeah, so now it's 6:55. We take a break. Yeah. Class, can I have your attention? We'll resume the lesson. Okay. We'll resume the lesson. Okay. So we move on to example 1.1-5. Okay. So in this case, we're actually given a setup like that. So this is one configuration. So you have this we have a robot manipulator. So as we keep mentioning, a robot manipulator have a base as well as an end effector. So the base is actually given a frame called B. So this is your base frame of your manipulator. And then the T is actually the frame attached to the end effector. So this is your manipulator. And then you have a tool on the table. So this frame of the tool is called G. You attach a frame G onto this board. And then the table itself, you actually take one corner of the table as the reference frame of the bench of the table. So this is labeled S. So a typical goal for industrial robotics is you want the end effector of the robot to actually pick up the tool. And then in this case, the robot need to know the location of the boot relative to its position. Relative to its position B, and so on. So this is a setup, this is a configuration. You have 4 frames, you attach them nicely. And then what happened here is, so in this case, you actually don't really have a global frame that actually comprises of this B and the table and so on. So the X over here, you may consider it as a global reference frame, but it's actually a reference frame for the table. So if we assume that you know BTT, meaning that you know this reference frame T with respect to the base frame. So this your robot is in this position. So you know the end effector with respect to B. So you know BTT. So you also know BXT. So BXT meaning that you know this the reference frame that you actually established for the table, or the frame that you actually attach to the table with respect to the base of the manipulator. So with respect to the base of the manipulator, you have your BXT. So now you also have you also know that the frame that's actually the board that's actually with reference to the frame X. So you have your XGT. So what really matters here is you want to determine the frame G with respect to frame T. So you need to know that so that the T can actually go in and pick up the G. So your TGT is essentially the position and orientation of the board relative to the manipulator hand. So what happened here is you use what we have learned previously, the consecutive transformation. So your TGT is equal to your TBT multiplied by your BXT multiplied by your XGT. So I have mentioned that the leading subscript of the homogeneous transformation matrix is the same as the leading superscript of the matrix to the right. So this one and this one is the same. So you can cancel off, this thing cancel off, this thing cancel off. You actually end up with TGT. So this is the TGT. So you actually can form a consecutive transformation in this manner. So, but what happened here is you do not know TBT. So just now, if you look at the question that is given to you, you only know BTT. You only know the end effector, the coordinate frame of the end effector with respect to the base frame. But you don't know the other way. But what happened here is the TBT is actually equal to your BTT transpose. So you have your BTT transpose, BXT, XGT. So with that, you will be able to determine your TGT. Okay. So what happened here is, if I have a ball in the air, you have a ball somewhere. So this ball is over here. And then we know the B ball with respect to B. The B ball with reference to B frame. So you know the B ball T. So the B ball T will be essentially equal to the TBT, the B ball T. So basically, if you want to determine any, you can essentially using these consecutive transformations to actually form the necessary matrix, and then from there determine the reference coordinates. So you have to think in terms of some form of cancellation taking place for each of such pair to give you the desired homogeneous transformation matrix. So in this case, this is a simple one because you basically have one manipulator and then you have a table in this manner. You may have more objects than this. Okay. So what happened previously is we actually we very much thinking of everything as a kind of frame transformations, transformation matrices and so on. So next, we actually look at we look at the interpretation of the coordinate transformation as operators. So the operators, so typical operators will actually comprise of the translation, rotations, as well as the transformations. So when we actually consider operator instead of what we've gone through just now, the matrices and so on, or the different frames, as we have mentioned just now, we only have one coordinate frame. So we don't move around the frame anymore, but we have one single coordinate frame, and then we are going to have all the different operator. So you have one coordinate frame, and then the first operator that we actually look at is, of course, your translation operator. You have to move from one point to another. So when you move from one point to another, you actually involve a movement in the x, y, and z direction. So when there's no movement in the y direction, your change of your distance in y, your movement in y is actually equal to 0. So you move a point in space, a finite distance along a given vector direction. So a vector AP1 is translated by a vector AQ. So your KQ will be QX, QY, and QZ. So this is your AP1. And then from here, you translate this point from this point to this point. So this P1 simply means that it's point 1. So don't read too much into it. So you have this point 1, which is actually with respect to frame A. You've gone through a translation AQ. The A over here is meaning that this translation is actually with respect to frame A. Then the result of the operation is you end up with a new vector. So you end up with a P2. So this P2 is with respect to the frame A. So AP2 is equal to AP1 plus AQ. So you have this AP2 over here. And then to write the translation operation as a metric operation, you have your AP2 equal to 1, 0, 0, 0, 1, 0, 0, 0, 1, QX, QY, QZ. And then you have this 0, 0, 0, 1 multiplied by AP1. So the QX, QY, QZ are component of the translation vector Q. So this is your translational vector. Some of you may not have been doing with matrices, rotation, and all those things for a long time, but it's okay. We will go from the basic. Yeah, you just have to go back and revise, and then there shouldn't be any problem. Yeah, no worry. Yeah, if you have question, yeah, let us know. Yeah. Okay, so this is translation. And then you have rotational operator. So you operate on a vector AP1 and change the vector to a new vector AP2 by means of rotation is your rotational vector. So bear in mind that when we talk about this rotational operator, it's about the origin. So it's the same as the rotation metric that we described earlier. We rotate a frame, rotate by RL relative to the reference frame. We actually initially assume that the two frames, the rotating frame and the reference frame, they are actually aligned. So we define a rotation operator RK theta. So we actually define RK theta. So RK. So you see that we actually write this RK as a bow. So AP2 is equal to RK theta AP1. So you do a rotation. K is the axis of the rotation. So you always use K to actually indicate the axis of the rotation. X axis, Y axis, Z axis, and so on. Theta is a degree, is the amount of rotation about the K. So if you actually look at the operator itself, you only rotate along one principal axis. So only one principal axis rotate one at a time. You don't have Rx. You don't have K equal to XYZ in one go. K is either equal to X, Y, or Z. So the operator that rotates about the Z axis by theta can actually be written in this form. So Rz theta equal to cosine theta minus sine theta, cosine theta, and so on. So you can go back and derive this. It's actually quite simple. But if you don't want, you can. If this is actually a right angle triangle, this right hand coordinate systems, the matrix will always be in this manner. For the exam, it's going to be an open book. You're allowed to bring in your notes, so don't need to memorize anything. You don't have to memorize the rotation matrix. Okay, so this is a 3x3 rotation matrix. And then if you actually make it into a homogeneous transformation matrix, you will have to add in an additional column, an additional row. So this essentially represents your translation. And then the additional row will always be 0, 0, 0, 1 in our context. Okay. So we'll look through this, we'll go through this via an example. So my figure 1-3 will have a vector AP1. So AP1 is 0, 2, 0. So we refer to this particular point. This is point P1. The A over here meaning that you actually refer to frame A. So you have your 0, 2. This is at 0. X is equal to 0 and Y equal to 2. Z is equal to 0. 0, 2, 0 transpose, because usually we tend to write a point as a column vector. So this is why you have a transpose over here. We used to compute the vector obtained by rotating the vector about Z by 30 degrees. So this is rotate about the Z. So the Z is actually pointing out of the finger, out of the paper. 30 degree refer to positive 30 degree. So counterclockwise positive. So you all remember counterclockwise positive. So counterclockwise positive, this is so this is why you have this positive 30 degree over here. So this is 30 degree positive. So if I have negative 30 degree, so meaning that it will be a clockwise direction. So you call this new vector AP2. So P2, we call this vector point 2, P2, and then A we refer to the coordinate frame A. So bear in mind that when we're actually doing the operator, we only have one single coordinate frame. So the rotation matrix which rotate vector by 30 degree about Z is given over here. So your Rz 30 degree will be 0.866 minus 0.5, 0.5, 0.866. This is your rotation matrix. And then when you have so this is essentially equal to the rotation matrix which describe a frame rotate 30 degree about Z relative to the reference frame. So they actually mean very much the same thing. So your AP2Z will be equal to Rz 30 degree A multiplied by AP1. So if you actually look at the difference between this operator and transformation and earlier rotation of frame, there's actually a difference. The difference in the way we write it. So this is no longer a matrix, but this is AZ 30 degree. This is an operator. But you will have the same results. So when you do the multiplication itself, you will actually end up with 0.866 multiplied by 0 plus 1 minus 0.5 times 2, 0 times 0. So you will get this vector minus 1. Then this one multiplied by this, you will get this. And this one multiplied by this, you will get this. Okay? Good. Then the transformation, when we talk about transformation operator, it will be actually comprised of both rotation as well as translate. So we define the operator T to be 1 to rotate and translate a vector AP1, point P1, we refer to A, to a new vector P2, we respond to A, or with respect to A. So AP2 is equal to T AP1. So the transform will actually rotate by R and translate by Q. So it's the same as a transformation that describes a frame rotate by R and translate by Q relative to the reference frame. They will get the same result. But both cases, but you may use both cases. You may use either cases, either as a frame transformation or operator throughout this course. So you need to know both of them. So for example, in example 7, 1-7, we show a figure. This is figure 1-4. You have a vector AP1. We wish to rotate it by about Z by 30 degrees and translate it 10 units in XA and 5 units in YA. So we want to find the AP2, where AP1 is equal to 370 transpose. So what happens now is you have only one reference, one coordinate frame. You are going to have motion. So you're going to perform one motion after another. So the first motion is you want to rotate Z by 30 degrees. So you rotate Z by positive 30 degrees. Remember, this is counterclockwise positive. So you rotate by positive 30 degrees. And then, so this is the initial point. So this is why you rotate 30 degrees. So this is a 30 degree positive. Yeah. So don't always assume that the point have to rotate from the frame, from the principal axis. So you rotate by 30 degrees, counterclockwise positive, and then after that after the rotation you have another translation. So this translation is actually 10 units in the x-axis and 5 units in the y-axis. So you actually end up with this point over here. So you have motion 1 and motion 2. So when you put them all together, so same thing, you have your T rotation matrix as well as a translation matrix. So your AP2 is equal to T multiplied by AP1. So you do the multiplication, this is what you have. So over here you can actually see that if you compare the answer, they basically is the same. The numerically is the same. There should be no difference. But you have a different interpretation. Okay, now we move on to other orientation representation. So earlier on, when we actually look at all these things, we are essentially having translation frame and all those things. We have actually represent the orientation of rigid body by 3x3 rotation matrix. So 3x3 rotation matrix, you have 9 elements altogether. So R11, R12, R13, R21, R22, R23, R31, 32, 33. So altogether there are 9 elements. So this is essentially consistent with the orthogonality condition. So you actually have 3 equations. So remember, when we start off the matrix, we say that the rotation matrix have to be orthonormal. Orthonormal also means that it's going to be unique length. So again, you have these 3 set of equations. So from there, you only have 3 of the 9 elements are independent. So we have said earlier on that essentially you only need 3 parameters to represent orientation. But you actually look at the equation and all those things, you actually find something, you actually see that there's actually, the only 3 elements are independent and the rest are actually derived from there. So what happened here is you have something called a redundancy. So you have more than what is actually necessary. So the different representation of orientation will require only 3 or 4 parameters. So the first other orientation representation will be the XYZ fixed angle representations. So XYZ fixed angle orientation we have talked about the roll pitch yaw before. So we saw an aircraft and then say that this is if you shrink left and right, you have your yaw, and then the pitch will be up and down, and then roll will be actually rotate along its axis. So you have your XYZ fixed angle representations. So the XYZ fixed angle representation will actually assume that same thing. We assume that the 2 frames are the frame A and frame B are initially aligned. So you first do a rotate. So the rotate will be by an angle gamma. So this will be your rotation angle along the x. And then after that, you follow by a second rotation along by beta. The beta will be the pitch, and then followed by a rotation along angle alpha. So this will be your yaw. So you have your roll, pitch, yaw, angle. So you have one rotation after another along. So each of these, the 3 rotations will take place about an axis in the fixed reference frame A. So the A have no change. So the B is changing. So we go back to the we are getting back to the frame transformation. So this is essentially consistent. So the roll, pitch, yaw is essentially a term started with the aerospace industry. So you have the roll, which is along the axis, up with the nose moving up and down is the pitch, and this is when you're swinging left and right is the yaw. So when you have this x, y, z fixed angle together, so your rotation matrix will comprise of A, B, R, X, Y, Z. So the A, B, R, X, Y, Z, meaning that your B will refer to A. So you have 3 angles over here together. You have your gamma, beta, and alpha. So this will be comprised of a rotation along the z-axis of the alpha, rotation along the y-axis by the beta, rotation along the x-axis by the gamma. So remember the order of the rotations. You first rotate along the x-axis, then the y-axis, then the z-axis, and hence you have this Rx, Ry, and Rz. Okay. So your Rx gamma will be 1, 0, 0, 0, Cx, C gamma minus C gamma, X gamma. So this C is actually referred to a cosine, and this refers to the sine. So this is the rotation metric along the x-axis. So in the beginning of the class, I showed the identity. This is exactly the same. And then you have the rotation metric along the y-axis. So this is the rotation metric along the y-axis. This is the rotation metric along the z-axis that we have been using. We have been using it as an example in the examples. So after you have them all together, you do the multiplications. So you have to multiply these two. Then after that, you multiply this with the product of these two. And then, so you will actually end up with this matrix. So this matrix are 9 elements. So this is C cosine, this is cosine alpha, cosine beta. So this is cosine alpha, sine beta, sine gamma, minus sine alpha, cosine gamma. So the x, so remember the notations. So the x and c actually denote the cosine and sine function respectively. So after you have done this, you have, so meaning that if you have an x, y, z and fixed angle representations, you will have you know the 3 angle, and then you will be able to derive the rotation matrix. So you have your x, y, z fixed angle. So the alpha, Bravo, the Bravo and gamma, they are fixed angle. So what about the inverse? So you have a transformation, and then the next thing here is you need to know the inverse. So the inverse, so a typical rotation transformation matrix will still be 9 elements. So you have a R11 to R33. So you want to find the 3 angle, the 3 fixed angle. So you want to find the 3 fixed angle, you match them up together. There will be 9 equations altogether. So you have R11 equal to this, R12 equal to this, and so on. And then with this, you will actually find that there will be altogether 9 equations, because corresponding one R11 equal to this, R33 equal to this. So there will be 9 equations altogether. And then there will only be 6 dependency, and 3 unknowns. So 3 unknowns are alpha, Bravo, and gamma. So you move on. We can actually try to determine. We can actually derive a way to actually determine this to find the unknown. So for example, my R33 will be equal to minus sine beta. So the beta itself will actually be equal to arc tangent to sine beta sine cosine beta. So the arctangent to xy essentially compute the tangent inverse y over x and use both the sines of both x and y to determine the quadrant in which the angle 9. So this is your arctangent. So if you have your arctangent to the x beta c beta, the 2 over here essentially refer to 2 axes. It's two dimension equal to 2. So it will actually end up with from here the sine beta itself will actually be equal to minus 3 1. So minus sine beta, the sine beta is equal to R31 from observation. So the minus sign is there, so you have your minus R31. So the cosine beta will actually be equal to plus minus. Cosine beta will actually be equal to plus minus square root of 1 minus R square 31. So from here, you will be able to determine your beta. So this is an illustration of tangent minus 1. So it's just in case you have, just for a quick recap. Okay, tangent minus 1, 45 degree. So you have determined beta. The next thing is you want to determine alpha. So you determine alpha, the same thing. You have your arctangent to sine alpha, cosine alpha. So sine alpha, cosine alpha, from observation itself, you will actually know that the cosine alpha, sine cosine beta equal to R11. So your cosine alpha will actually be equal to R11 divided by cosine beta. And similarly, you can actually determine that the sine alpha is equal to R21 divided by cosine beta. So it's tedious. You just make and match. And then after that, you work on the grammar. So you have same thing. By observation itself, you can actually know that the grammar with the sine grammar will actually be R32 divided by cosine beta, and cosine grammar will be R33 divided by cosine beta. So with that, the inverse transformation will actually give you this, will actually give you the solution for the three unknown. The parabola, alpha, and gamma. So, but actually, if you look at it itself, you can actually have two solutions. So you have your plus minus square root of R11 square plus R21 square. So if your R31 is equal to 1, if the magnitude for R31 is equal to 1, R31 is equal to 1, it will actually imply your R11 equal to R21 equal to R32 equal to R33 is equal to 0. So what happened here is the solution is going to degenerate, and then degenerate will actually end up with something called mathematical singularity. So you can't find the inverse. You have a singular. You have a singularity problem. So in that case, the difference of alpha and gamma may be computed in this manner. Okay? So you will actually end up with a matrix like that. And then if you actually equate them together, if your R31 is equal to plus 1, your beta will actually be equal to minus 90 degree. And then your R31 is equal to minus 1, your beta will actually be equal to, the R31 equal to positive 1, your beta will be minus 90 degree. Your R31 equal to minus 1, your beta will be 90 degree. So the beta is actually is the rotation along the y-axis. It's the angle of rotation along the y-axis. So this is one way. This is one representation. It's known as the XYZ fixed angle. But of course, you can have XYZ is fixed angle. You can also have XZY. You can have different combinations. So you can have a set of different combinations. You can have a set of different combinations, and then so end up you will have this is a fixed angle. You have altogether the 12 different combinations. So you can actually, so we go through the x, y, z. You can have x, z, y. You can have y, z, y, x, z, and so on. So they all together you end up with 12 combination. And then these are the matrices for all the different 12 angle from combination. Okay.
Is that gamma, beta, alpha specific to the rotation axis?
Sorry?
And is the volume of the gamma, beta, alpha specific to the specific axis? I mean, like.
Yes. Yeah. Yes. Yeah. Yes. The alpha bubble gamma will still be the bubble will still be with the will rotate around the x. Yeah, it's a sequence. Yeah, it's a rotation sequence. So the rotation sequence, you will actually end up with a different matrix. So these are the 12 angle set that you get to see on the notes, on the supplementary notes. So this is from a textbook. Pick up from the textbook. Okay, so what we have gone through earlier on is a fixed angle. So now we actually move on to something called an Euler angle. So for the Euler angle, we start with a sequence z, y, and x. So you have the fixed. So Euler angle and fixed angles are different. So the difference between the Euler angle and fixed angle is that a fixed angle meaning that you have, yes?
Could you explain the 12 fixed angle set again?
12 fixed angle, okay. Maybe after I talk about the Euler angle and then I go back again. Okay? Yeah, thank you. Because they are kind of related. Yeah, I'll go back to it. So at this point you remember the sequence, and then you know that the fixed angle is meaning that the specific fixed angle, the axis does not change. Okay. So when we talk about the Euler angle, the rotation is performed about an axis of the moving frame. So rather than the fixed reference frame A. So for example, over here, if we have the Z, Y, and X Euler angle, so initially same thing. You have your frame. You have both A and B, a 9. And then after that, you will actually rotate. You will actually rotate in this case, you rotate along the Z. So you rotate along the Z by an alpha. So you rotate along the Z by an alpha. So you have this rotation. And then after you have this rotation, you have your new ZB, XB, and YB. So this is your new one. Then after that, you rotate along the beta of the B frame. So the moving frame is you are actually rotating with respect to the moving frame. And then after that, followed by the X, which is again you are rotating along the moving frame. So the rotation is performed about an axis of the moving frame B rather than the fixed frame A. So you have this Euler angle. And then what happened here is same thing, we recall our consecutive transformation. So your AB error is equal to AB prime error, B prime B double prime error, B double prime B error. So you have a multiplication of this. And then when you actually solve it in the form of operator, so you have your Z prime, Y prime, X prime, alpha, bubble, beta. You have your Z alpha, Y beta, X gamma. So you rotate along the X, rotate along the y, and rotate along the x. So you multiply together, you actually have this form. So if you compare this and the result obtained earlier on with the x, y, and z, you actually can see that the results are the same, but they're actually done in the opposite direction. Okay? So bear in mind that the order of rotation is always important. So if I have a composite rotation of Ry, Rz, and Rx, it does not equal to Rx, Ry, and Rz. So for example, if I have two frames over here, so these two frames, I have the reference frame, the x, y, and z. So this is x, y, and z. So this is the reference coordinate frame. This is the world frame. This could be a body frame as well. And then I have another frame, u, v, and w. So u, v, and w, the u, v, and w could be a robot frame, coordinate frame. It could be another body coordinate frame. The object P may rotate about the axis of either O, x, y, z, or O, u, v, w. So it doesn't mean that you have to be rotate. You always have to rotate within the reference frame. And then for the deviation and so on, we usually start with the O, x, y, z, and O, u, v, w usually aligned. If they are not aligned, you need to do a pre-multiplication to actually make them align. So for the exercise, you need to keep in mind that if the body, the u, v, w move, you have a new position and orientation. If this movement is with respect to O, x, y, z, you need to do a pre-multiplication. A pre-multiplication meaning that your new t will equal to the motion multiplied by the O, x, y, z, and O, x, y, z, O, u, v, w transform. So that's meaning that before the transformation itself, you need to do the motion. Okay. And then if I have the movement is actually with respect to O, u, v, w. O, u, v, w. So this is the robot frame. You will have to do a post multiplications. So meaning that your motion, your rotation motion, and all those things will actually happen after the transform. So these two rules. So you have to remember these two rules for your exercise. So please work on the exercise question, and then I will on next Monday I will release the solution, and then you can actually compare. You can look at the working and then compare the solution, and then compare your working with the solution. Okay, now we look back. Now we move back to the Euler equation, to the Euler set of the Euler angles as well as a fixed angle. So the angle set convention, this is so when you have your Euler angle set as well as the fixed angle set, they're all together known as the angle set convention. So altogether you have 24 convention. So the 24 convention will perform 3 rotations about the principal axis in a certain order. So there will be child for the Euler angle set, and then the child will be for the fixed angle set. So there's a duality of the fixed angle set with the Euler angle set. So just now we have done, and we show that if we do a fixed angle x, y, z, the result is actually equal to the same as z, y, x. Okay. So there's a duality. So this is the term duality come from. So usually to indicate that this is a Euler set, we will put x prime, y prime, z prime. And then this alpha will actually be referred to rotate along the x-axis, beta y-axis, gamma z-axis. Okay. So all these will be with respect to each other axis. So you have all together the Chow-Euler set. So this alpha x prime, beta z prime, and gamma y prime. Okay, so this is what we have gone through just now, the deviation. And then you have the Chow angle set given over here. Okay. Okay. X, Y, Z. So X, Y, Z. Okay, it has X, Y, Z, X, Z, Y. So there are three cell combination. There are three 1, 1. So there are three combinations. So if you move around them, you can only have child combination. You exclude all those things that actually rotate by itself. So you can only have a maximum of child angle. Yeah, you can't have more than that. Okay, so if you have imagine if I have we'll move on to the next one, which is the equivalent angle axis representation. So you have the angle set, so you have your fixed angle, Euler angle. So now we actually come to something called equivalent angle axis. So just now the student, okay, if I did not answer your question, maybe you can come to see me afterward. Just now the student that asked about the angle set. Sorry. In the document, in the PDF document. Yes. Yeah. The child fixed angle set. Yes. Bravo, beta, alpha, yes. Yeah, the Rxyz. So this Rxyz, okay, so the Euler angle we indicate by x prime, y prime, and z prime. The fixed angle we indicate by xyz. Okay, so if we indicate by xyz, if you indicate by xyz, so you do a first, you rotate along the fixed axis of x, and then after that you rotate along the fixed axis of y, and then followed by along the fixed axis of z. So if you rotate along the fixed axis, of x, you have Rx gamma. And then if you rotate the fixed axis along the y, you have your Ry beta. And then if you rotate along the alpha within the fixed axis of z, you have this Rz alpha. Okay. Okay. Yeah, the sequence of rotation, if I rotate x first and then followed by y, so this is the first time, this is the first rotation I rotate, then multiply by y, then multiply by z. So it's always this sequence. Yeah. Sorry? y is y. Other y, y beta. Okay.
Why they have x, y, x, but they don't have
Oh.
y, z, y?
Oh, y don't have y, z, y. Okay, so this is. Okay. So the question, yeah, okay. So the question is here. So you have this combination xgx, and you have this combination yxy. So why don't you have a combination of yzy? Huh? Why don't you have a combination of yzy? So if your yzy, if you go to this Euler angle, yzy will still be your y prime z prime y prime. Yeah. So it's a derivative issue. Yeah. So you just cover all of them. Okay. Yeah. Sorry, let's move on. Yeah. Okay. So we come to the last one. Which is the equivalent angle. Okay. So far what we are looking at is actually a three-parameter representation. So the next one that we're actually looking at is something called the equivalent angle axis. So for equivalent angle axis, we actually have something called Euler parameters. So it's a 4-parameter. So it's a non-minimal representation orientation. We know that we only need 3 parameters to represent an orientation. So now you actually need 4, so you have 1 additional parameter. So therefore, this is not minimal. So because you have 1 more. But you do have an advantage for it. With this non-minimal, you actually want to take away the ambiguity. So you want to make sure you have a unique number. So what is the equivalent angle axis? So an equivalent angle axis meaning that any rotation matrix can be represented by choosing a proper axis and angle. So this is based on the Euler theorems on rotations. So meaning that if this is a fixed frame A, we have frame B, and then if we want to rotate frame B, we can actually rotate it according to an axis. So this is K. So this K is a vector. It's an axis. And then this K is an axis. This is an axis. It's a vector. So it consists of 3 parameters. It's a direction. The axis have a direction. And then you need this angle. So theta. So you actually end up 4 parameters. So the 4 parameters of real number will consist of the scalar. So this is theta, which is known as the angle of rotation, and 1 unique vector. So the k cat. So usually when we indicate a unique vector itself, we will put a hat over here. So when you actually look at the notes, I may not go to them very clearly. So if you see a hat down there, it's the representation of a unique vector. So of course, make sure you actually read in context. So this is the axis of rotations. And then in all cases, this is according to the right-hand rule. So we are not going to derive the equivalent angle axis. So the matrix will actually be given in this manner. So R K cap theta. So you're going to rotate along this one by angle theta. You will actually end up with a matrix given over here. So your angle, your v theta over here is actually equal to 1 minus cosine theta. And then the unit vector k hat, the A over here, meaning that it's actually we refer to the A frame. So you have your kx, ky, kz transpose, because we represent a vector by a column vector. It's a unique vector, meaning that the k hat is actually equal to 1. The magnitude of the a hat is actually equal to 1. So the angle, the size of the theta, will actually determined by the right-hand rule. So when you actually have a small angular rotation, the axis of rotation will actually become ill-defined. And then for the you may still end up with a non-unique. You will end up with a non-unique representation if you have, for example, in this case, your r minus k hat minus theta is equal to r k hat theta. So in this case, so meaning that if I have this, I will probably have another one in the opposite direction. So this is k hat, this is minus k hat. And then counterclockwise positive, so you look in counterclockwise positive, and then over here will be clockwise. If you rotate along the minus k hat. So we look at an example. So a frame B is described as follows. So if initially you have A and B together, and then we rotate B about the vector AK 0.707, 0.7070T. So, and then this axis K, the axis of rotation, pass through the origin. So you have to bear in mind that you need to have a proper selected axis and angle. So there are a set of conditions with that. So one condition is that the axis have to be passed through the origin. So with that, you have by an amount theta equal to 90 degrees. So it's supposed to give the frame description on B with reference to A after the rotation. So A and B are initially aligned. So you do same thing, your AK 30 degrees. So you are given the matrix, and then we are not going to derive it. So you substitute in the value itself. This is what you have. And then there's no translation of the origin because basically they are essentially the two frames are still, there's no translation in the two frame. So there's no translation in the two frame. You have 0, 0, 0. So you have rotate AK 30 degrees, substitute the value, you will actually end up with this set of number. So this will give you the ABT. So meaning the transformation of B with respect to A. So which is what given over here. The description of B with reference to A. With respect to A. Okay? So you put in the value itself, you will actually get the answer. So what frame B, if I have a frame B described in the following manner, so frame B is initially the same as A. We rotate B about the vector AK, passing through the point AP123 transpose. So what happened here is we have a problem now. Just now we just mentioned that the axis of rotation should pass to the origin. But what happened here is we have a case where the axis of rotation doesn't pass to the origin. So how? You need to resolve it. You need to resolve it by reduce the problem to the axis to the origin. So you need to define an additional frame with origin line on the axis and then solve a transformation equation. So meaning that you did the same as what you have done earlier on. You have your A prime, so an intermediate frame that's actually in between. To move it to the origin. So we define two new frames, the A prime and B prime. So these are obtained by translating A and B respectively to point P, and then B and B prime can be treated as if they are mount on the same rigid body, and then A and A prime are fixed in the space. So if you look at the diagram, it will be something like this. So you need to need to reduce the problem to a point where k pass through the origin. So you have so this is your initial A, B. So you have your A prime, B prime. So your A, B, A prime, T. So your A prime, T is essentially a translation. So translation, in this case, you translate by 1, 2, 3. And then the translate back will be -1, -2, -3. So P will be on the point of. So P will be on the axis of if P is on the axis of rotation, then we rotate B prime relative to A prime. So this is a rotation about an axis which passes to the origin. So from here we actually can apply the equation that we have done, the matrix that we have done earlier, that we have mentioned earlier. And then after that you have your A prime T, the rotation matrix, and you will have the A prime B prime over here. And then after that you have to do this consecutive transformation. So you do this consecutive transformation, the same thing, you have your ABT equal to A prime T, A prime B prime T, B prime B T. So this and this cancel off, this and this cancel off, you have your ABT. So multiply them together, this is what you have. So basically, it's a set of metric manipulations. So if you look at this, you can actually see that after rotating about the axis K, which is not through the origin, the plane B actually separated from A. So the plane B is actually separated from A. So they are no longer aligned. They are no longer attached. Okay. So a rotation about an axis that does not pass through the origin will cause a change in position plus the same final orientation as if the axis had passed through the origin. So we have the equivalent angle axis. Now we look in the forward direction. Now we actually look at the inverse problem. So same thing. So the inverse problem meaning that if you are given the matrix A, B, R, so meaning that the rotation matrix of B we refer to A. So you are supposed to find the angles of angle of rotation theta as well as the axis of rotation K hat. And this K hat have to be referred to A. So this is the inverse problem. So given the metric, you want to find the parameter. So you know that the ABR can actually be represented, consists of 9 elements, and then each of them is an orthonormal vector. So you have your NX, NY, NZ, OX, OY, OZ, consists of three column vector. So if we can, another way of writing these 3 column vector will be NX, NY, NZ, OX, OY, OZ, AX, AY, and AZ. So this is equal to this that we have, the equivalent angle axis metric. So same thing, you do the equate. You equate them together. So you do the equate them together, you can form the diagonal element. So this is the diagonal element. So this and this is the diagonal element. You can actually find that the trace of A and B, ABR is equal to 1 plus 2 cosine theta. So the trace of a metric A is defined to be the sum of the elements on the main diagonal. So if you put them together, you will actually find that this is essentially equal to 1 plus 2 cosine theta, and then cosine theta is actually equal to half tray ABR minus 1. So if you look at this itself, you can actually find that there's possibly the theta will have a plus minus A. So there's a possibility that the theta will have two solutions. So if the sine theta is not equal to 0, if sine theta is not equal to 0, the sine theta, this is the sine theta. If sine theta is actually not equal to 0, you from the nz and ax element, from these two elements itself, you can actually determine your ky. From oz and ay, you can determine your kx, and nx and ox element, you can determine your kz. So this is by comparison. So you will be able to determine this. So this is in the condition that the sine theta is not equal to 0. What happens if sine theta is equal to 0? Sine theta is equal to 0, this will become 0, so ky will become infinity. So there's a condition here, your sine theta cannot be equal to 0. So there's a possibility of two unique solutions. So as mentioned over here, there's a possibility of two unique solutions. So these two unique solutions will be represented over here. So you have your AK hat, and then in the opposite direction, you will have your AK hats minus. So you have this counterclockwise theta. You again over here, you have your clockwise minus theta. So in general, you will actually end up with two solutions. So if theta equal to 0 degree, your ABR will actually be an identity matrix. So this is intuitive. If your angle of rotation is equal to 0, there will be no change. So if there's no change, you will end up with an identity matrix. So your rotation matrix is an identity matrix. So this one is intuition. So there's no rotation. Essentially, it's an identity matrix. You can have your k prime can be any axis. So if your theta is equal to 180 degree, you will actually end up with this matrix. If you do the calculations and deviation and all those things, you will actually end up with this matrix. And then if you look at this matrix itself, you'll find that this matrix is a symmetric matrix. What is a symmetric matrix? A symmetric matrix meaning that this is a diagonal element, this will be equal to this will be equal to this, and this will be equal to this. So the upper half and lower half is the same. So when your upper half and lower half is the same, your inverse of a symmetric matrix will actually be equal to its transpose, and then which is actually your original matrix in this case. Okay, when you have a symmetric matrix, the transpose will actually transpose back to itself. Follow? So if you equate them together, you will actually end up with kx, ky, kz equal to this situation where you have your plus minus over here. So the plus minus here, one of the solution will be for A1, will be for k hat, and the other solution will be for your minus k hat. The interesting thing is if all diagonal elements are 0. So all diagonal elements are if all off diagonal elements are 0. So this is a diagonal. So off diagonal element will be this, and this. If these other elements are equal to 0, so these other elements are equal to 0, you still have a symmetric matrix. Then your kx, ky, and kz will actually be equal to 1, and then, yeah, kx will actually be equal to 1, and ky and kz will actually be equal to 0. So your AB error essentially, your AB error will actually end up with something like this. So this is equivalent angle axis representation. And the last one we have is something called Euler parameters. So the Euler parameter again is not minimal representation. So you also use 4 parameters instead of 3 parameters. So the Euler parameter will be able to solve the non-uniqueness problem. So this is not unique. So because you have your plus minus over here, you have you are likely to have 2 solutions in 2 different quadrants. So the Euler parameter will be able to solve it. So same thing, you have the Euler parameter will actually be defined in this manner. You have your epsilon 1 to epsilon 4. So epsilon 1 will equal to ks sine theta over 2, epsilon 2 equal to ky sine theta over 2, and so on. So kx, ky, and kz are the equivalent axis k hat. So they are related. But theta is no longer the angle of rotation. Theta is known as the equivalent angle. Theta is the angle of rotation, which is also known as the equivalent angle. But what happened here for the Euler parameter is that you have these 4 parameters. So these 4 parameters are interesting. These 4 parameters are not independent. So not independent meaning that if the change of one value will affect the rest of the value. An independent parameter meaning that if you change one, the rest, it doesn't actually affect the rest. So they are not independent, and you have your epsilon 1 square plus epsilon 2 square plus epsilon 3 square plus epsilon 4 square equal to 1. So when you have this equation itself, you can actually visualize a hypersphere in 4-dimensional space. So a 3-dimensional space, every point on the surface of the sphere. A 4-dimensional space, meaning that you can actually expand out. So the Euler parameter will remain in the interval -1 to 1. So the epsilon 1 to epsilon 4 will have this value, -1 to 1. Will have the value within there. So if theta equal to 0, if your theta is equal to 0, so cosine 0, your epsilon 4 is actually equal to 1. So if epsilon 4 is actually equal to 1, then the rest must be equal to 0. Okay? So based on the equivalent angle set equation, and then the definition of this Euler parameter, you actually come up with the AB error. You have the AB error given here. So you with the epsilon 1 being defined over here, go to a set of trigonometry deduction. So you use a cosine theta equal to 2 cosine squared theta over 2 minus 1, and so on. And then you actually end up with this error epsilon. So this R epsilon will be defined as 2 epsilon 4 squared plus epsilon 1 squared minus 1, and so on. So you see, you are actually transforming from this equivalent angle axis equation matrix to this matrix. Follow? So we are not going to go through the deviation. So with all this deviation itself, eventually you will end up with this matrix. So again, we look at the inverse problem. The inverse problem meaning that if you're given the matrix, you want to find the epsilon. the Euler parameter. So there are 4 of them. So epsilon 1 to epsilon 4. So to find the epsilon, you actually need to use something called the sign function. So the sign function, the sign of x, the sign function sin x is equal to 1 if x is greater or equal to 0, and sin x is equal to minus 1 for x is actually less than 0. So this is your sign function. So again, you match this with this, and then you match this with this, and then you the sign function on the right will be illustrated by Rick Bock. So it's to extract the sign of the epsilon 1 based on the element R32 and R23, R32 and R32. So based on these two correspond with this, you will be able to determine the epsilon 1. So again, it's a mix and match, and then after that, to a complex set of metric manipulation. So you will end up with the epsilon 1 and epsilon 4 given over here. So the unique thing about this Euler parameter is that there will be only one unique solution for a given rotation matrix. So if you have only one unique solution, you will be able, it's good for implementation, so you will know that this is the only solution that achieves it. You don't have the uniqueness. You don't have the ambiguity. So this is why we want to have the Euler parameters. You don't have the ambiguity. You have one set of unique solution. So at the end of the day, all these, you need to implement them. You need to implement them in a robust simulations so that you can determine the parameters and so on. So this is why we study the Euler parameter instead of stopping at the equivalent angle. And then there are actually, another characteristic of this Euler parameter is that it's actually implicitly assumed that the epsilon 4 is greater or equal to 0. So in this case, we only consider the theta between minus pi and pi. So no singularity compared to the angle axis representation. Okay, so next week we'll move on to, next week is a Chinese New Year holiday. So the week after, we'll move on to the kinematic modeling. Please bear with me for please give me another 5 more minutes. We will move on to the modeling of the manipulator arm. So what we have gone through here is we talk about the frame. So we attach the frame to the link. So you see we only attach the frame to the link, not to the joint. So this is one frame to this link, to another, third, and so on. And then there's a frame, and then there's a frame to the n effector. So this is so the whole idea about this thing is you want to determine the n effector position and orientation with reference to the base frame. So this is so what we did earlier on the mathematics and so on is actually to provide us to do the kinematic modeling. We'll talk about that after the week after. So it's important that you actually have a good grasp of the mathematical fundamental. So please. So this one is a basic. It's kind of like a quick mentioning of how the deviation is about. If you are interested, you can actually refer to this book. And then so this is a quick summary of what we've gone through on the different representations. So for rotation metric A, B, R, you have 9 parameters. So bear with me for summary. So you have 9 parameters altogether. The angle set convention, you can have 3 parameters. So x, y, z is low pitch yaw angle. It's also known as a yaw pitch yaw angle. They are altogether 12 fixed angle set and 12 Euler angle set, so altogether 24 of them. You have and then we also talk about the equivalent angle set representation. So this equivalent angle set representation, there will be 4 parameters. So bear in mind that you actually start with the plane coincide with the known plane. And then you rotate B about the vector A hat by an angle theta according to the right-hand rule. You have the Euler parameter. So same thing, the Euler parameter is also 4. The Euler parameter is also 4 parameters, so it's not non-minimum. So it's an extension from the equivalent angle set. So you have epsilon 1, epsilon 2, 3, and 4 defined in this manner. So this is the normality condition. So the axis of rotation will always be equal, the magnitude will always be equal to 1. So this is a unique vector. And then your epsilon 1 square, epsilon 2 square, and so sum of it will actually be equal to 1. So essentially, you have a point on a unique hypersphere in 4D space. This is the exercise 1. So the first 2 questions are essentially asked. You can get the answer from the notes. So there are definition and so on. So what is plane and degree of freedom? So you should know by now very well on what is degree of freedom. So you have all this. You have a vector A rotate by about ZA by theta degree, and subsequent rotate about XA by another degree. So it's proposed to give the rotation metric that accomplishes this rotation in the given order. So these 2 are different. So bear in mind. And then you also have these other equations. So remember the 2 rules that I mentioned to you. So you have to do the pre-multiplication and post-multiplication in answering the question. Okay. So there are altogether 8 questions. Yeah. So this is the homework for this week. I'll release the solution on next Monday. Have a good holiday, everyone. Bye-bye.